I am Shudeshna Banerjee, Professor in the Department of Mathematics, Jadavpur University, Kolkata. In this course of lecture, we shall study about the theory of integral equation, which is a very important topic in mathematics. Now, the question comes, why do we study integral equations and how do the integral equations occur? Now, we know that any physical phenomena, when translated in terms of mathematical language, we get initial value problem or boundary value problem involving a governing differential equation, ordinary differential equation or partial differential equation, along with initial conditions and boundary conditions. Now, the integral equation arises in a natural way while trying to solve a large variety of initial value problem or boundary value problem involving ordinary differential equation and partial differential equations. Consequently, the initial value problems and the boundary value problems in mathematical physics are handled by reducing them to integral equations. Now, if we know the solution of integral equations, then using the solution of this integral equation, we can find out the solution of the corresponding initial value problem or the boundary value problem. So, there is a close link between differential equation and integral equation, and we will see that integral equations serves as a important tool in solving the initial or boundary value problems. Now, the origin of integral equation may be attributed to famous mathematician Niels Henrik Abel, who in 1826, while studying a well-known problem in mechanics, produced an integral equation which is known as Abel integral equation. Later, in 1896, V. Volterra, famous mathematician, and in 1900, another Swedish mathematician, E.I. Fredholm, systematically developed the theory of integral equation. Now, in this course of lecture, we have divided the whole content into 5 chapters. The first chapter is an introductory chapter, which is again divided into 3 modules. In the first module, we shall learn what is an integral equation and various forms of integral equations. Here, we shall learn what is an integral equation. An equation involving an unknown function y(x) of a single variable x, where x lies in the closed interval a and b are real constants, is said to be an integral equation for y(x) if y(x) appears under the sign of integration. Here in the following, we have given some examples of integral equation. In example 1 and in example 5, we see that the unknown function yx appears only under the sign of integration, whereas in examples 2, 3 and 4, the unknown function appears under the sign of integration as well as it appears freely. Now, in all the 5 examples, apart from the unknown function yx, there are 2 other functions kxt and fx which are assumed to be known at present. In examples 1, 2 and 3, we see that the limits of integration are constants, whereas in examples 4 and 5, we see that the upper limit of integration is a variable. Again, in example 3, we see that yt, the unknown function, appears non-linearly under the sign of integration. So, the first classification comes about the integral equation being linear or non-linear. The integral equation in which the unknown function appears linearly is called a linear integral equation, otherwise it is a non-linear integral equation. So, the integral equations in 1, 2, 4 and 5 are linear integral equation, whereas in example 3 the integral equation is a non-linear integral equation. In this course of lecture, we are concerned with linear integral equation and we study about the theory of linear integral equation. Now, the general one-dimensional linear integral equation for an unknown function phi x can be written in the form as given in equation 1.1, where c is a constant which takes up either 0 or 1. Lambda is a constant which is the parameter of the integral equation. The function kxt is a known function. It is known as the kernel of the integral equation. Also, the function which appears on the right hand side, that is fx, it is also a known function and is known as the forcing term. Now, in the linear integral equation, if the forcing term fx is equal to 0, then this integral equation is called homogeneous integral equation, whereas if fx is not equal to 0, then it is a non-homogeneous integral equation. Again, in the integral equation 1.1, we have said that c takes up values either 0 or 1. If c is equal to 0, then this integral equation is known as integral equation of first kind, which is given by integral a to b kxt phi t dt equal to fx, x lies in the interval a to b. Again, in the integral equation 1.1, if c takes up the value equal to 1, then the corresponding integral equation is known as the integral equation of second kind, which is given by phi x plus lambda integral a to b kxt phi t dt equal to fx, x lies in the interval a to b. So, in second kind integral equation, phi xt appears freely apart from being under the sign of integration, whereas in first kind integral equation, the unknown function phi t appears only under the sign of integration. Next, if the limits of integration appearing in the integral equation 1.1 are constants, then this integral equation is known as Fredholm integral equation. But if any one of the limits of integration is a known function of x, then the corresponding integral equation is called Volterra integral equation. We go back to our 5 examples. Examples 1 is a linear integral equation of first kind. Example 2 is a linear integral equation of second kind. And in example 1 and in example 2, the limits of integration are constants. So, example 1, the integral equation is Fredholm integral equation of first kind, and in example 2, the integral equation is Fredholm integral equation of second kind. We come to the example 4 and 5. In example 4 and 5, the upper limit of integration is x, the variable. So, example 4 is an integral equation of second kind of Volterra type, and in example 5, the integral equation is first kind integral equation of Volterra type. So far, we have learnt about what is an integral equation and its classification, like what is a Fredholm integral equation, what is a Volterra integral equation of first kind, integral equation of second kind. Now, we shall classify the integral equations according to the behavior of the kernel. We have classified the integral equation as Fredholm integral equation or Volterra integral equation. Now, we shall classify the integral equation according to the behavior of the kernel kxt of the integral equation. If the kernel kxt of the integral equation is such that the double integral a to b mod kxt whole square dx dt has got a finite value, then the kernel is known as regular kernel and the corresponding integral equation is known as regular integral equation. On the other hand, if the kernel kxt of the integral equation 1.1 is of the form kxt equal to fxt divided by x minus t to the power alpha, where fxt is bounded in the interval ab cross ab with fxx is not equal to 0, and if alpha lies between 0 and 1, then the integral equation is known as weakly singular integral equation, and the kernel kxt is said to have weak singularity at x equal to t. Again, if in the integral equation 1.1 the kernel kxt has the form fxt divided by x minus t, where fxt is a differentiable function of x and t with fxx not equal to 0, then the integral equation is known as singular integral equation, and the kernel kxt is said to have a strong singularity at x equal to t, and the integral a to b kxt phi t dt is understood in the sense of Cauchy principal value as given by limit epsilon tend to 0 integral a to x minus epsilon kxt phi t dt plus integral x plus epsilon to b kxt phi t dt. Next, if the kernel of the integral equation is of the form kxt equal to fxt divided by x minus t whole square, where fxt is a differentiable function with fxx not equal to 0, then the integral equation is known as hypersingular integral equation. The kernel kxt in this case has got a very strong singularity, that is hypersingularity at x equal to t. In this case also, the integral, or rather any integral with hypersingular kernel has to be given a meaning. Here the integral a to b psi t x minus t whole square dt has to be understood in the sense of two-sided Hadamard finite part integral of order 2 defined by limit epsilon tend to 0 integral a to x minus epsilon psi t x minus t whole square dt plus x plus epsilon to b psi t x minus t whole square dt minus psi of x plus epsilon plus psi of x minus epsilon divided by epsilon. In module 1 of chapter 1, we have learned what is an integral equation and its various classifications. Now, I will mention that the literature on second kind integral equation is quite rich as compared to the first kind integral equation. The literature on first kind integral equation is very limited. So, with these few words, I conclude the module 1 of chapter 1.